So good morning, everybody. I hear you did have a good discussion about how to detect neutrons. So that's excellent. Maybe we can chat about some of those things during the break or at the barbecue tonight. In my second lecture, what I want to do is focus in a little bit more. The first lecture was very generic about particle detection technology, where we tried to sort of very quickly cover a very broad range of the physics behind how you detect different types of particles. What I want to do now is I want to delve into a specific example of this, the EPIC detector for the EIC. And I want to do several things here that might seem a little bit unusual. We're at a particularly useful time, I think useful for you in the design of the EPIC detector, that it is still fresh. And in many ways, we are still trying to define what the EPIC detector is. So in addition to talking about the kinds of detector technologies that are used, I also want to show you how those detector technologies are selected to work together in concert to balance off the strengths and weaknesses of each other, so that the combined detector is in many ways greater than just the sum of the parts. I also want to show you a little bit of what happens under the hood, right? Which is to say, how do you actually come together and form a collaboration like this? And how do you go from a conceptual design with maybe a scribble on a napkin or some PowerPoint blocks to the design of a real detector with all of the compromises and trade-offs that entails? The reason I want to do that is because I'm very well aware that many of you will probably build your career analyzing the first data from the EIC, and I don't want you to curse us too loudly when you're looking at the performance and the trade-offs that had to be made to design the detector in the first place. So that's the plan for today. In order to introduce the EPIC detector, we first have to go back and think about what we're trying to do, right? What we want to do is we want to study the structure of matter at the electron-ion collider, the structure of hadronic matter in great detail, right? By studying its structure both in physical space and in momentum space. And in order to do that, the tool that we use is deep inelastic scattering. Or one of the tools that we use is deep inelastic scattering. And in deep inelastic scattering, what we do is we send in an electron. It exchanges a virtual photon with one of the partons inside the hadron, be that a proton or neutron inside a nucleus. And by studying that interaction, we know, by looking at that interaction, for example, we know an enormous amount about the final state. That's one of the things that is tremendously useful about this interaction. If I just measure, for example, the outgoing energy and angle of the electron, and I measure nothing related to the scattered parton, I already know, for example, the momentum fraction of that parton, right? I can map out the proton in great detail. If I measure more about the final state, I can learn more about the structure of the hadron. I can learn about correlations. I can learn about the distribution in physical space, etc. So what we need to do is we need to design a detector that can detect very accurately, with high precision, the scattered electron, as well as the hadronic remnants or the scattered remnants from the hadronic state. Okay, so that's our goal. The EIC science mission, then, I just wanted to remind you of this, is we want to study nucleon properties like mass and spin and how they emerge from quarks and their interactions. We want to understand how color-charged quarks and gluons interact with the nuclear medium. And we want to study a high-density nuclear environment and see what impact that has on the interactions, correlations, and behaviors of quarks. I suspect this has already been introduced to you, but I just wanted to cover it again to sort of start from the big picture. What are we trying to achieve? Because at every stage, we're going to be looking at what kind of a detector do I need to be able to do this physics? And because the physics program is extremely broad, worrying about the structure of nucleons, the propagation of partons, all the way up to nuclei, you have to be able to design an extremely flexible detector that can cover not only a wide range of physical phase space, but a wide range of observables to be able to access all of this physics. Keep in mind, the EIC project right now only includes one detector. We hope that there will be a second detector. It will almost certainly not be there on day one. right? And so that means we need to design a detector that is capable of pursuing the entire EIC science program. We can't just lop off part of the program and say, the other guys will do that, right? In fact, depending on how things go, we might be it. Okay? All right, again, just to remind you some of the capabilities of the EIC machine, we're going to be colliding electrons and hadrons. So if we think about electrons and protons, we're looking at an electron energy from 2.5 to 18 GeV. That dictates to us what the center of mass in these collisions looks like, because we're going to be colliding with protons from 40 to 275 GeV. So right away, you see from the energies that the collisions are asymmetric, right? It's not like RIC, for example, where the detector is sitting in the center of mass. The center of mass is going to be moving in our experiment, right? And it will be at different points for different collisions, because the center of mass between, for example, the electron and the scattered parton will depend on the momentum fraction of the parton, right? So we're going to be a collider detector, right, that's looking at an asymmetric system where the center of mass will be moving in our detector from collision to collision. Okay. We have to be able to handle high luminosity. Todd talked about that yesterday. We'll talk about it more today. High luminosity is what enables you to look at more and more rare processes, right? So the number of events you see is the luminosity times the cross section, right? If you have a very low cross section, you're looking for a low probability process, you need a lot of luminosity, right? Polarization. I won't say much about spin today. I know you've got some other lectures on that, but polarization is important both for the electron and ion, and we're capable of looking at an ion species from proton to uranium. Yeah. Question? Oh, I'm sorry.
Sorry.
There was a question. Okay. All right. So what are we looking at? We're looking at electron scattering, right? And electron scattering is comprised of a variety of processes. As I mentioned, if we take a look at what's called neutral current deep inelastic scattering, we're exchanging a virtual photon or possibly a virtual Z boson, and we're exchanging that with a parton inside the proton. And in neutral current DIS, just the detection of the scattered electron with high precision tells you everything that you need to know about the event kinematics. That's what makes DIS so beautiful. This will allow us to measure things like parton distributions in nucleons and nuclei, the same as the Hera Collider did in the 90s and early 2000s. One of the advantages that the EIC will have is it will be able to do that in a slightly wider kinematic phase space. Okay, so we'll be able to map the same phase space that Hera did and extend the edges a little bit. But we'd like to be able to learn a little bit more. Now, there's also, I mentioned charge current DIS. We don't say much about this, but here it's more complicated, of course, because when you exchange to W, the electron becomes an outgoing neutrino, and the only way you know about the event kinematics is to reconstruct everything, right? So you need to know everything about the hadronic remnants in the final state. That means you need detector acceptance everywhere because you can't miss anything. Okay, so that's more complicated. In semi-inclusive deep inelastic scattering, now things get more complicated. Semi-inclusive, right? Inclusive means you average over everything. Semi-inclusive, right? So inclusive means I average over everything that happens here and all I measure is a scattered electron. Semi-inclusive means, I try to detect a hadron that arises from the scattered parton, right? And then I average over everything else. Once I detect a hadron from the scattered proton or scattered hadron, this gives me more information about what's going on inside the structure of the proton, and that's where I can extract things like momentum correlations, spin and momentum correlations, etc. The most difficult process in electron scattering is to take a look at a process where you scatter a virtual photon off of some colorless exchange from the proton, right? So, for example, you can think of that as a pomeron. Does anybody know what a pomeron is? Right? People heard of a pomeron before? Pomeron is just a colorless QCD object, right? The easiest way to think about it is a two-gluon exchange where the color cancels out. okay? Because of that, the proton doesn't change its identity, right? But it's scattered, and it's scattered at some small angle. And the photon interacts with that pomeron and produces hadrons or photons in the final state, right? So this is, for example, the beginnings of things like deeply virtual Compton scattering, right? This is an exclusive process. Exclusive processes have small cross sections, right? Because I'm now not looking at a wide range of interaction channels. I'm focusing everything down, right? And then you need high luminosity for these. You also need to be able to detect all of the particles in the event, including that scattered proton, right? And guess what angle that proton comes out with respect to the beam? A couple of milliradians, right? So now I need to learn everything I can about that proton, just a little itty bit away from the main beam, right? And be able to detect that, okay? So this is, I hope you see an enormous dynamic range in the kinds of things that you need to be able to measure in the detector. So I wanted to just advertise a little bit for people who are interested, the EIC Yellow Report. The EIC Yellow Report was a process that began in 2018, 2019. It was about a year-long process. And the community came together to define not only the scientific measurements that needed to be made, building on the National Academy of Sciences report for the EIC, but the physics requirements and detector requirements to actually make those measurements, right? How are we going to do this? What kind of detector do we need to build to be able to do this, right? What are the properties of that detector that we need to build to be able to do this? They define things like the tracking resolution that was required, the calorimetry resolution that was required, okay? So if you're interested in a rundown in a lot of detail, particularly the section on the detector is very, very, very informative in terms of the thinking that went into how to design this detector. The point I want to leave you with is the design of the detector for the EIC began with the physics first, right? And we've been trying to maintain that all along. Define the physics and then define what you need to build in order to do it, right? It's not defined by, well, somebody over here has a lot of money and wants to build a calorimeter, let's do that, right? So that's not the way this began. All right, so let's talk about the kind of detector requirements that we have for an EIC detector. So this is a very schematic representation of an EIC detector. Here you have a central detector, you have what we call a hadron end cap and a lepton end cap. In this diagram, the hadron beam is going from left to right, and the electron beam is going from right to left, okay? They collide here in this central detector. And what this diagram tries to show you is, in a very simplistic way, where do the particles go, okay? So for a scattered electron, right, low Q squared, right? Low Q squared means low momentum transfer. The virtual photon has a low momentum transfer. That means that the electron doesn't deviate very much from its original direction, and the low Q squared electrons go into this direction. So they basically scatter and they go into this part of the detector. In this part of the detector, then, we need very good electron identification. We need to be able to separate it from backgrounds, and I'll talk about that in a bit, and from hadronic remnants. As we go up now, right, to higher and higher Q squared, these events are more and more rare, but notice that the electron gets knocked more and more even backwards, right? The momentum transfer is so strong that it knocks the electron in the other direction, okay? So we need good electron identification, not only in the lepton end cap, but in the central detector. What else do we need? Let's think about the quark, the struck quark that we're going to interact with. We interact with a quark which has a certain fraction of the momentum of the proton. We refer to that as X, right? X can go from 0 to 1, right? If the momentum fraction of the quark is very large, right? Then again, you have this situation where the momentum of that quark is very large compared to the electron. It gets smacked, it doesn't deviate very much, and it goes forward into this hadron end cap. Okay. If, for example, that has a smaller and smaller fraction of the momentum of the proton. And for example, physics like saturation requires you to look at very low momentum fraction of the proton. That quark gets knocked backwards all the way into the lepton end cap. So my lepton end cap with my exquisitely tuned detectors for detecting electrons also have to be able to measure and separate hadrons and not get them confused with the electrons, right? Likewise, my high Q squared events, I have to be able to separate those out from the jet of particles that comes from a high X quark. So this isn't clean. It's not easy. Everything is all mixed up. I would really prefer my hadrons to go into one set of detectors and my electrons to go into another. But I don't get that. The kinematics doesn't give me that. Okay? So I have to design an integrated detector to be able to do this. There are a set of requirements to do this. And I list them here. They're listed in a table, a very complicated table in the yellow report. I've tried to break them out a little bit in a way that's a little bit easier to read. So if we start in the very central region of the detector, I need a vertex detector, right? I need to be able to track particles that have decayed from a secondary vertex away from the primary vertex, right? For example, I need to be able to detect charm, right? Charm is a heavy quark, bottom quarks are heavy. I need to be able to measure those because those can tell me a lot, for example, about parton propagation in the nuclear environment, okay? So I need a vertex detector. That vertex detector has to have a very low material budget. Why do I need a low material budget? What happens if I put too much material in? I block stuff from getting to the detectors. Remember, this is the innermost part of my detector. And if I put too much material there, the particle can interact with me or it can scatter. And remember, I'm trying to get a precise measurement of its momentum out of these tracking detectors in the inner part of the detector. I create a fundamental systematic limitation, right? That means if I put a certain amount of material there, I'm accepting the fact that I could never do better than X in the momentum resolution, right? Now, so that's a trade-off between what technology can do and what I want, right? What I want is a zero mass, 100% efficiency detector that suspends itself in space without frames or cables. I'm not going to get that, okay? And so I have to be able to live with something in between. I need a tracker that also extends into the end cap region, into the lepton region and hadron region, because I need to be able to track leptons and hadrons. I need particle identification. I'm going to spend some time on this today because we didn't get to the particle ID section of the talk last time, but I need to be able to not only say, it was a charged track with charged 1 and momentum of 2.743 GeV. I need to be able to say that was an electron, or that was a kaon, or that was a pion, with a high degree of certainty. The reason I need that is because that's how I tag the flavor of quark that I interacted with. Okay? And I need to be able to do that to pull apart the structure of the proton. I need electromagnetic calorimetry. I need to be able to measure not only electrons, but photons over a wide angle. And I need to be able to separate those showers from the hadrons that might be coming in these events. I need a hadronic calorimeter, right? In order to measure the energy of charged hadrons. And it's kind of funny. I don't really need a calorimeter that can tell me with high precision the energy of, let's say, a proton or a pion, because I'll measure the momentum really well in the tracker. What I need that hadronic calorimeter for is to measure things like neutrons, halongs, neutral hadronic energy that doesn't get tracked anywhere else. Okay, so it's a different requirement. I need very forward and backward detectors. So you notice that these angles go down to a pseudo rigidity of 4 and -4, or within 2 degrees of the beam line. I need to go closer than 2 degrees to the beam line, right? To detect, for example, the scattered protons in that exclusive process. Finally, I need a data acquisition and readout electronic system that is triggerless. And I'll say a little bit about that in a bit. Does anybody know what I mean by a trigger in a data acquisition system? Right? A trigger is something that says, an interesting event happened. You should read out the whole detector, right? You've seen the range of this physics program. Do you think it's possible to design a trigger, a set of electronics that acts on a time scale of tens of nanoseconds and can select with 100% efficiency every physics process I'm interested in? No way. Can't be done. You can do that. You can do that if you're looking for, let's say, the Higgs at the LHC, right? Big, whopping energy deposits, clear examples. Here, I'm looking for things that are all the way from pipsqueaks of interactions to huge interactions, and I want it all. So I have to design a triggerless data acquisition system. Yeah.
On the previous slide,
Uh-huh.
I just want to know if does the center of mass need to coincide with the collision point of the two beams?
The center of mass is moving always in these collisions, right? So imagine, let's say, proton-proton collisions, right? Two equal energy beams, and they're happening right in the center of my detector. My center of mass then is stationary in the center of my detector. It's not moving. That's usually why you build a collider detector, right? Here we have an electron with lower energy than the proton. And every time I have a collision, it's not interacting with the whole proton, it's interacting with a fraction of the momentum of the proton. So sometimes the center of mass is moving this way, sometimes it's moving this way. So every collision, the motion of the center of mass is different. And that's why, for example, you see that the hadrons go all over the place and the scattered electrons go all over the place. What's RIC? So RIC is a symmetric machine, right? So RIC, for the most part, a symmetric machine. So when they do AA collisions or PP collisions, that's symmetric in the center of mass. When they do PA collisions, to first order, right? They're the same momentum per nucleon, right? And so like a PA collision, right? Really what's fundamentally happening in a hard scattering is, a proton is interacting with another proton. The system is on average, the center of mass is not moving, right? Does that make sense?
It does. So that's why I was wondering, because in EIC, the center of mass will be moving. So
Yep. And that's the nature of the asymmetric, it's an asymmetric collider, right? Yeah.
I ask why we have requirements to have the crystals, I ask about electromagnetic calorimetry. Why it's different? We would like to have different technology for backward and forward. And backward is, crystal.
Yeah. Performance and money, right? So you could look at this and say, lead tungstate's fantastic, right? I love lead tungstate, right? I'm going to put lead tungstate everywhere. It's expensive. There's one place in the world that makes it, and they only make so many at a time. And in fact, to build the backwards calorimeter, to build all the crystals we need for the backwards calorimeter, we actually have to get special permission from the DOE to place that order early so we can get them by 2028, 29, 2030. So we're going to consume the world's production capacity to first order for lead tungstate crystals. So they're real, there's what you want, and then there are real fundamental trade-offs that you have to make. So you try to match the detector technology for what you need. I need very good resolution here. I need good resolution here. I need maybe okay resolution there, right? And so you pick the technology that's matched to the needs. So another questions, yeah.
You mentioned now PA and AA collisions. What would be an equivalent of Q from EIS PA collision?
So it's not defined in the same way, right? It's not defined in the same way because what you have, you don't have that simple interaction of a virtual photon, right? So it's a good question, right? I think the answer I would give is it's just not defined in the same way. You can, for some classes of interactions, you can define a momentum transfer, say between the two partons, but there's a wide range of possible interactions and higher orders and everything else. So it's just not as easy as Alexa may have a better answer.
From the point of view of technology, if you say have proton collision produces one particle, for instance, and the transverse momentum of this particle, the first order is associated with what they think is the underlying process. But of course, there are ambiguities there, and that's why in phenology usually we change this scale by a factor of 2 multiply or divide it and see how the result comes back. But what John said, it's true. We don't really know in proton what's the underlying scale, because the process is much more complicated.
Because you have some momentum fraction on some momentum fraction, you don't experimentally have any information on the final state kinematics. Right?
Unless it's a Drell-Yan.
Unless it's a Drell-Yan, that's true. That's true. And that's why Drell-Yan is another one of these excellent processes. Yeah.
The barrel imaging calorimeter is the barrel moved forward.
Which, I'm sorry?
The barrel imaging calorimeter.
The barrel calorimeter is in the central detector. We call that the barrel. Right? Because it's a cylindrical, I'll show you a diagram of it. Good, yeah.
Why, what the asymmetric nature will have something to do with the detector?
I'll show you in a bit.
Oh, okay.
This is just another example of the requirements and how they're related to the physics processes. So for DIS, for deep inelastic scattering, good old fashioned deep inelastic scattering, you can ask yourself, where do most of the electrons go, right? Well, most of them go into the end cap, but there's some part of the cross section that sends them into the barrel and even into the hadronic end cap. If you want to measure deeply virtual Compton scattering, that's one of these exclusive processes, where does the virtual photon, or excuse me, where does the final state photon go? Well, a lot of them go into the electron end cap, but a lot of them go into the barrel. But when they go into the barrel, they're relatively low energy, right? So now I have to be able to detect with high resolution a low energy photon and separate it from other stuff. That's hard. What's that other stuff? For example, if I look at the deep inelastic scattering events that produce a pi zero, where's the pi zero photons go? Well, they look like this, right? So a large number of those are overlapping my deeply virtual Compton scattering photons, and I have to separate them. Another way to look at it is if you look at deep inelastic scattering events and where the electron goes as a function of pseudo rapidity. So this is backwards, this is less backwards, and this is closer towards mid rapidity. What else could fake out an electron? Well, you can have pions that can fake out an electron. And so if I need to detect, let's say, low energy electrons, I need a rejection for pions of something like 10 to the fourth. That means out of 10,000 pions, I only get faked out once. That's a big ask. Okay? That's a big ask. Okay. I want to say a brief bit about the detector design process. So we had this yellow report. The yellow report then resulted in a call for proposals. There was a year-long effort by the community to define these project proposals. There were 3 proposals sent in: Athena, Core, and ECHE. And in March 2022, there was a review, an external review, a blue ribbon panel, which took a look at both detector proposals. Of course, we had a meeting in December. They gave us homework over Christmas, and then we met again in January to show them the homework. So nobody got a Christmas that year. In the end, the ECHE detector was chosen. But there's a point I want to make here in that Athena and ECHE were the 2 major competitors, right? And they were really honest efforts by both parts of the field to define a way to do this physics, right? In many ways, the kinds of detector technologies that they used were very similar, but they started from a fundamentally different point. ECHE said, we're going to reuse the Babar magnet that already exists, 1.4 Tesla solenoidal magnet. Athena said, nope, we need a 3 Tesla magnet with a great big large bore so we can put more detectors into it. They both started from fundamentally different points, and the detector evolved from there. Neither one of these were wrong. Athena could have been evolved to do the physics. ECHE could have been evolved to do the physics. But you need to pick something and you need to start from somewhere, right? So you'll see this as you go through your career. There will be these big selections, right? And usually it's not a selection of who's right or wrong. It's a balancing of cost, benefit, approach, likeliness to succeed, risk, right? But whenever you see somebody, quote unquote, lose, right? That's people who had really, really good ideas, right? and an external entity needed to make a judgment about what way to go. Okay. So in the end, we did a design, in the end, let me go back. In the end, we came together as a community and we formed the EPIC collaboration out of both ECHE and Athena. And in the process of forming the collaboration, we reevaluated the technical design of the detector, starting with ECHE as a baseline and pulling in really neat ideas and technologies that were in the Athena detector, right? So we were fragmented as a community, we fought for a year, and we needed to come back together and heal those wounds. And we did that with science, right? Oops, going the wrong way. We did that with science, but designing the EPIC detector. And so this is the basic design of the EPIC detector. It starts with a new 1.7 Tesla solenoid. Now notice, Athena wanted a 3 Tesla solenoid. ECHE wanted to reuse a 1.4 Tesla solenoid. And after we worked on it, we ended up building a new 1.7 Tesla solenoid. Why? Cost and risk, right? You have to do what's achievable. Yeah,
Administrative question.
sure.
The two ideas, like one to reuse the bar magnet and then one to, create a new one.
Yep.
Was that kind of like those ideas kind of delegated to these groups, or did the groups kind of independently on their own say, this is what we would like to do?
No, there was a genuine disagreement. Now I'll show some of that. Based off of things like the tracking resolution that was required, there was a group that said, got to build a new magnet. It's got to be huge, right? And there was another group that said, I don't think you have to build a new magnet, right? Both sides were sort of pushing the limits, right? And that's good. They pushed the limits of what was available and they worked for a year to see how far it would go. There was a genuine disagreement about what was the right approach, right? And as you'll see, in the end, it turned out to be something in between, right? It's kind of the fun. It uses a silicon maps tracker, and I'll describe that in the inner region. So this is a silicon tracker like we talked about yesterday. And it uses a series of micro pattern gas detectors in the outer regions to supplement the tracking. In the inner region, it has comprehensive particle ID with a whole different set of technologies from time of flight and 4 different ring imaging Cherenkov counters. I'll describe that for you in a bit. But that covers essentially the entire phase space of the experiment, and it has calorimetry surrounding the entire experiment. Okay. Now, whenever I show this, one of the things I like to tell people is I've been extremely dishonest with you, right? I showed you the central detector for EPIC. That's not EPIC, right? EPIC is not 8.5 meters in the IP6 interaction hall. EPIC is actually highly integrated with the collider itself. And instrumentation for EPIC actually extends from minus 40 meters all the way to plus 40 meters along the beam line. That instrumentation we call the far forward and far backward instrumentation, and that's required, for example, to either monitor the beam and luminosity of the machine, capture very low Q squared electrons that don't even go into the central detector, and to capture, for example, these protons that are scattered at small angles with respect to the beam line. So in many ways, EPIC is fundamentally different in that the machine and EPIC are designed to work together from the beginning, right? You take a look at the LHC. Have they branched out and started putting things along the beam line? Sure, but they didn't start that way. So EPIC and the EIC have been designed together from the very beginning. One of the neat things about EPIC is it utilizes a crossing angle. Crossing angle means that the beams don't come in and interact head on. They cross at 25 milliradians, right? Why do we do that, right? That sounds complicated. Why would we go through all the trouble to do that? So if you think about it, if you want to bring the beams into collision, right? They're 2 separate rings, so you have to bend them and put them on the same axis so that they come in together. When you bend beams of electrons, what happens? Right. Synchrotron radiation. And from the standpoint of an experimental, synchrotron radiation, bad. So there's no way to bend them so that they come head on without putting that synchrotron radiation fan right into your detector. Right? So by not doing that, right, you don't have to have big dipoles close to the experiment, and you gain yourself a little bit of space, and the beams cross at an angle. What you also get is the beams come out at an angle, And so you have space as the beams separate to be able to put instrumentation in the beams. So it buys you two things, but it does something really bad. And I suspect Todd will talk about more about this in his talk today, but it does something really bad because if you look at the bunches, and this is sort of an idealized version, right? The bunches aren't really the same size, but you look at how they cross, right? If you don't do anything, they don't overlap fully. If they don't overlap fully, you don't achieve the high luminosity. If you don't achieve the high luminosity, you're wasting money, right? Because it costs millions of dollars, close to millions of dollars per week to run this thing. And if you're 20% less luminosity, you have to run 20% longer, it's 20% more money. Money, 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 okay? So what's done is a really clever idea that comes from the machine people is to use something called a crab cavity to rotate the bunch. And so you rotate the bunches so that they come in at an angle, and when they come in at an angle, they fully overlap. What this means is that there is a correlation in the detector between, so that they don't all occur on the z-axis. They come in and occur on a line that crosses the z-axis. And where they occur on that line tells us about the timing of the interaction in the bunch. That gives us something called the T0. We know the start time for the interaction. So not only does this give us high luminosity, but it gives us another handle that we can use experimentally. So I just want to show the far forward detectors. These are a set of detectors that are designed to track, for example, scattered protons at very, very small angles. This is called the B0 combined function magnet. It's probably a accelerator physicist nightmare, right? Because you're very tight to the experiment here. And so what you need to do is you need to design a combined magnet so the electron beam and the hadron beam both go through it and get the bend that they need, right? So it's a very sophisticated magnet to start with. And then the experimentalists come along and say, and yeah, I want a big gap in there so I can stick my tracking detectors, right? So this is a tour de force. There are also things called Roman pots and a 0-degree calorimeter, which captures, for example, neutrons, which go straight down the beam line, right? And off momentum detectors supplement this tracking. We have far backwards detectors too. The far backwards detectors are how we monitor the luminosity of the machine, right? So here we take the higher energy portion of the spectrum of synchrotron radiation, Bremsstrahlung, and what we do is those photons will come out of the machine at an exit window, right? Now, coming out of the exit window, some fraction of them will convert into an E plus and an E minus. In fact, at high luminosities, there's so many of them, that's no good to us. So what we do is we have a magnet to sweep them out of the way. And then we have a region filled with helium to transport those photons, those Bremsstrahlung photons, to a second converter where we convert just enough of them so that it doesn't blast our detectors to death. And then we measure the energy of the E plus and E minus. That allows us to monitor the luminosity of the machine, right? Because the Bremsstrahlung is directly proportional to the interactions between the electron beam and the proton beam, higher intensity, more Bremsstrahlung. We also have what's called a low Q-squared tagger. Sometimes the electron has such low momentum transfer that it goes down the electron beam line. That's really interesting physics. It's not deep inelastic scattering physics, it's called photoproduction physics, but it's also interesting physics that we need to know about. We capture those electrons in a low Q-squared tagger, where we can tag all the way down to something like a Q-squared of 10 to the minus 3, right? Can't go further because then we pick up a whole bunch of radiation from Bremsstrahlung. So we can look at very, very low momentum transfers. Let me start in the barrel now and tell you a little bit more about the design of the barrel of the EPIC detector. Make sure I'm not running out of time here. We have two inner barrel tracking layers, or excuse me, we have three inner barrel tracking layers, two vertex layers, which are optimized to be very close to the beam pipe so that we get a measurement of the track as soon as possible. That's important for measuring these displaced vertices. Okay. We have a third layer, which sits a little further out. That starts to measure the bend of the particle. And then we have two longer R layers, which will use new sensors that are designed to measure the bend of the particle and give us the momentum. In the forward and backwards region, we have silicon disks that are designed to track particles going into the forward and backward region. Notice there's a gap here between these. Right? There's always a gap. There's always a gap, right? I can't design a tracking system that is gapless. I can't design a tracking system that is gapless because the cables for this detector need to come out somewhere, right? The cooling to keep the detector from burning itself up needs to come in somewhere. The signal cables need to come out somewhere. Just to show you the technology that we're using, we're basing the inner two layers off of these ITS3 MAP sensors. The neat thing about these is the pixels are of order 10 microns, right? So we get a measurement which is better than 10 microns in precision, right? Amazingly precise measurements. They also are very thin. They have about 5% of a radiation length. Remember, we're in the innermost region. We don't want to screw the particle up. 5% of a radiation length. They do that by making these silicon sensors and then thinning them down to 50 microns. And then they bend them into a hemispherical shape and mount them in a frame so that you have a limited frame and you don't have material overlapping each other in order to get a cylindrical structure. In the outer layers, we have to accept a larger amount of material, like 55% of an interaction length of a radiation length, simply because the outer layers are larger, right? We can't afford to do everything with bent silicon. We have to use a different technology, and it has to be supported, right? So it has to have a frame. So it's not the silicon sensors that contribute to that. It's the frame, it's the support, it's the surface. We use gaseous trackers in the outer layers. Those are about 20% of an interaction length. They have a resolution of about 55 microns, and the combined momentum resolution looks like this. So the dashed line is the requirement from the yellow report, and the measured points are the simulation of the EPIC tracker. So notice in the forward region, we do pretty good with respect to the PWG requirement. In the mid region, we do pretty good. In the backwards region, we don't do so good, right? So does that mean EPIC is doomed to fail? It's a fundamental limitation. In a solenoidal field, as you go more forward, right, you get less and less bend from the solenoidal field because the field has to turn in order to return the flux. There are limitations to how many trackers and how well you can measure the particles track. A tracker will practically never achieve this momentum resolution, right? And so you say, well, is that throwing some physics on the floor? No, because what we need to measure here are electrons. And so we can supplement this by, instead of measuring the momentum very accurately, we can measure the energy of the electron very accurately. So we have a very good electromagnetic calorimeter that picks up the weight of that requirement. I want to say something about silicon detector readouts because this is something people don't really understand. I want you to memorize this diagram. I'm kidding. Silicon detectors, right? You think, wow, why doesn't everybody build these things? I got a 20 micron space point, right? That's fantastic. The problem with silicon detectors as they are right now is the time that they integrate over, right? And this is not like charge integration that you think of in another kind of detector. What happens when a silicon pixel is hit, it sets a discriminator, right? So if it's above a certain threshold, it sets a value out of the discriminator. That's easy, right? That's fast. The problem is you read them out by strobing the detector when you latch the results of the discriminator, and then you transfer that to a buffer to be read out. That latching time is 2 microseconds. The beam crossing time at the EIC is 10 nanoseconds. So you see the problem. Every time I read out my silicon detector, I collect the results from 200 beam crosses. Now, that's not so much of a problem from the interaction standpoint, because the interaction standpoint is always the maximum interaction rate is 500 kilohertz, right? But backgrounds, synchrotron radiation, beam gas backgrounds, I integrate those over 200 crossings. So I'm going to get a lot of extra hits in my silicon tracker. I need to be able to sort that out. And the way I sort that out is with these micro pattern gas detectors. So the tracking system has an inner layer called a micro mega. A micromega is a tracking detector where it does amplification with a mesh, right? So there's a mesh which is standing off of a pillar, and then you have an anode strips down here, and that mesh provides the high electric field that is the amplification layer. So again, it's an evolution of this concept that we saw with multi-wire proportional chambers. The nice thing about these detectors is they can be very fast. They may only have a 50 micron spatial resolution, but they can be very fast. The nice thing about micromegas is they can be bent into a cylindrical geometry. So in the inner region, I can build a cylinder. In the outer region, I can use a different technology called micro R-wells, which basically combines a gem foil. So you see they're using a gem foil here to do the same kind of thing that was done with a wire mesh. So now I have all these hits in the silicon detector. I can find tracks, but I don't know which one happened in the crossing I was interested in. But if I match them to the hits in the micro R-well and the micromega detector, now I know which tracks came from the crossing I was interested in, and I can throw out all the other junk. Right? That's how the detectors need to work together to be able to provide the physics measurements. Let me say more about calorimetry. I'm going to be careful not to run out of time here. So calorimetry, again, we have comprehensive calorimetry. In the backwards region, we have a simple hadronic calorimeter, which is a steel scintillator sandwich. It's a very simple design. The idea is just to catch hadronic energy that might be going in that direction, right? We have a very complicated backwards electromagnetic calorimeter built around lead tungstate crystals. Again, I'll show you the resolution, precision, exquisite resolution for electrons, which supplements in part for the fact that the tracking resolution is very difficult in that region. We have a barrel electromagnetic calorimeter, which is actually a reuse of the CFNS calorimeter. And in the central barrel, the electromagnetic calorimeter here is a design which uses lead and scintillating fibers combined with silicon sensors in the inner region in order to provide a high resolution capability to resolve 2 photons coming from pi0 decay, right? Ordinarily, those would overlap and you would only see one shower. But if you can see the shower develop, you can say, that blob of energy came from 2 photons. And in the forward region, we have a high granularity tungsten scintillating fiber EM-cal and a high longitudinally separated H-cal with a high pseudo rapidity insert. So you can see we're using different technologies in different regions to reach different performance requirements. To show that, this is the calorimetry performance in different regions for the expected calorimeter performance based off the technology that's chosen. So if we start here, this is the forward electromagnetic calorimeter, and you see that the simulations of the forward electromagnetic calorimeter sit here, and these bands, right, are the required performance in order to do the physics, right? So we exceed the required performance due to the physics, not by a ridiculous amount, right, but by an amount that we can absorb some imperfections if things don't turn out like our simulations. The same is true in the backwards EM-cal, and notice the resolution that we're getting down to, a couple percent, right? Less than a few percent, so energy resolution of less than a few percent. This is the barrel EM-cal. Again, you see very good energy resolution, and in fact, it exceeds the momentum resolution of the tracking above 15 GeV or so. Tracking is interesting. The tracking resolution gets worse as the momentum gets higher, right? Because the particle bends less. But calorimeters do better as the energy gets higher because you average over more interactions, you get a better result. So there's always a point where you can take and combine the track information with the calorimeter information and get a better measurement. And then this is the outer H-cal and the LF H-cal, and you can see they also exceed the performance requirements. But you can see here, you know, the stochastic term is here. It's like 2.5% over root E, and for the electromagnetic calorimeter. Here for the H-cal, 75% over root E. So there's a massive difference between how well you can do between electromagnetic and hadronic calorimetry. I'm going to zip through some of these a little bit. This is just the backwards hadronic calorimeter. It's made out of these non-projective lead tungstate crystals. I showed some things about the lead tungstate crystals in yesterday's lecture. The barrel H-cal, I showed this because mine. I was the level 2 manager for this for CFNS. I love this picture because this is my student, Noah Applegate. sort of patiently waiting for me to go away so we can get back to work. The barrel EM cal, I mentioned the ability to have these AstroPic sensors. These are sensors, so they're unusual in silicon land, right? They're very low power sensors, so they don't generate a lot of heat. If they don't generate a lot of heat, we can embed them in a calorimeter, right? And use them to provide high precision space points as the particles begin to shower inside the calorimeter. These were actually developed for a NASA space mission, and we're appropriating them for use at the EIC. The forward EM calorimetry, this is a tungsten sci-fi calorimeter. I showed you the S-Phoenix calorimeter yesterday. It's very similar to that. The longitudinally separated forward HCal is actually separated in depth. And the reason for that is the particle showers that go in this direction are highly compressed. So you may get many particles that overlap each other when they shower in the calorimeter. By looking at how they develop in depth, we can try to separate them and take advantage of combining tracking and calorimetry. Okay, particle identification. This is what I wanted to get to today. So sometimes it's not enough to know that a particle passed by. You need to know the identity of the particle. Is it an electron, a muon, a proton, a pion, or a kaon, etc. There are many techniques. For electrons, one of the easiest techniques is to match the momentum and the energy, right? The electron has a negligible mass. So roughly speaking, the momentum that I measure in the tracking should be equal to the energy I measure in the calorimeter. Usually what's done is to take an E over P ratio, which should peak at 1, and you can put cuts around that and throw anything out that doesn't fit within that range. Pions can occasionally fake you out, so that will only get you so far, and you need to add some additional capabilities to that. You can reconstruct the decay by calculating an invariant mass. A pi 0 decay to 2 photons, well, you can reconstruct the invariant mass and you get a peak at the pi 0, right? You can also do this with charm, right? And you can statistically reconstruct, let's say, D0 meson. You can look at penetration depth for muons. We talked about that yesterday. If you want to identify things like pions, protons, kaons, you need a different technique, and you can use things like time of flight or things like Cherenkov radiation. Cherenkov radiation is radiation that's emitted when a particle travels faster than the speed of light in a medium, right? My undergraduates always get confused when I talk about this. Not traveling faster than the speed of light in a vacuum, that's an absolute limit. But in a medium, the speed of light is different based off the index of refraction of that medium. But a particle can travel faster than that. And when it does, it emits radiation. And this radiation is called Cherenkov radiation. And it's emitted at a characteristic angle related to the index of refraction and the velocity. So if I can measure that radiation, I know the velocity of the particle. If I know the velocity and the momentum, what else do I know? Mass. I know its mass, and the masses of pions, kaons, protons are different. So I can identify them this way. There are many ways to do this. You can just detect the light. There are thresholds for this. It only happens above a certain momentum, and that depends on the particle mass. Or you can detect the ring and use the ring to reconstruct the velocity. By the way, has anybody seen these beautiful pictures where you see like a nuclear core and the water is glowing blue? That's Cherenkov radiation. All right, that's Cherenkov radiation in the water surrounding the core. Okay, so for the EIC, we need particle identification over a very wide range. In the backward region, we need to be able to identify pions, kaons, and protons, and photons and gammas up to 7 GeV, and separate electrons and hadrons up to 18 GeV. We need, in the mid-rapidity region, we need to go up to 8 GeV for electrons and hadrons and 10 GeV for pi kp. And in the forward region, all the way up to 50 GeV and 20 GeV for electrons and hadrons. And we do that by combining a number of technologies. At the lowest, the slowest particles can be identified by time of flight, right? The slower the particle, right, the more time it's going to take to get to a certain detector. But of course, the faster it goes closer and closer to the speed of light, right, then everything looks the same. So for slow particles, we can use time of flight. We can use then different Cherenkov detectors in different regions to get us all the way up to this required particle ID threshold. So we have a number of particle ID detectors, again, covering 4 pi. There is what's called a proximity focused rich in the backwards direction, a high performance Dirk in the forward direction, a dual radiator rich proton direction, the hadron direction, and then time of flight with a new technology called ACL-GADS. The HP Dirk is an interesting beast. It's actually based off of these fused silica bars, high purity fused silica bars. These bars are organized into boxes which surround the barrel of the detector. And what happens is when a charged particle enters the bar, it creates Cherenkov radiation. And that Cherenkov radiation is trapped by total internal reflection inside the quartz bar. It travels to the end of the detector, where we have a set of focusing lenses and an expansion volume that expands the image from that bar out onto a series of photodetectors. And the image you get is not a complete ring, but you get an arc. By measuring that arc, you're able to tell the velocity and momentum of the particle. Yeah.
You mean by fused in this context?
Very pure, very, very pure quartz, right? Very pure quartz. So with absolutely minimal imperfections, right? This is very, very good. Whoops. This is very, very good at electron-hadron separation and hadron particle ID. It does require that your photon sensors actually sit inside the magnetic field. We know silicon photomultipliers are no good for that, so you need to use a different technology to make that happen. The proximity focusing Rich sits in front of the backwards region, and its primary responsibility is to be able to separate, again, electron-hadron and hadrons pi kp. This is a simple device. It uses aerogel. Does anybody know what aerogel is? What the space shuttle tiles were made out of, right? It's very, very thin, very light silica, right? You can adjust the index of refraction to be very, very, very low for this, which allows you to get these low thresholds. So you have an aerogel radiator, and you have that focused on a large sensor plane where you read out the photons. You also have a mirror in here, which recaptures some of those photons and sends them back into the acceptance. So you capture an image of the other side of the ring that you would have lost, right? That increases your detection efficiency because typically we're only talking about handfuls of photons, 5, 10 from Cherenkov radiation. Can't lose any. The detectors that are used are called LAPPDs or HRPPDs. I wanted to show you guys these because they use a microchannel plate. And if you remember from last time, we talked about how phototubes work. They have these dinodes, right? Where the electron goes, creates more electrons, more electrons, more electrons, more electrons. They don't work in a magnetic field, right? Because the focusing to the dinodes doesn't work. This has basically a plate, a metal plate, low work function plate, and the holes are drilled at an angle. And that angle actually acts like a diode. So you get amplification of the electrons. Okay. EPIC will be one of the first detectors to use LAPPDs, HRPPDs, certainly one of the first particle physics detectors. There's a neutrino experiment, Annie, which is testing them right now. And we're going to use them in two ways. One is to detect the Cherenkov photons, but the other is going to be to detect the photons that come from the glass. So you get Cherenkov photons from the glass in the front of the HRPPD when the particle that creates the Cherenkov photons goes through it. So you get a very intense spot. HRPPDs have very good timing. So this is going to serve as our timing detector as well. So you can see how we've combined functionality. The dual radiator Rich, in order to get that large coverage over a wide degree of area, it uses both aerogel and a gas, C2F6, chlorofluorocarbon gas, in order to get momentum separation all the way up to 50 GeV. So this will actually produce two rings. It will produce one ring from the aerogel and one ring from the gas. I mentioned ACL-GADs. ACL-GADs are a new type of silicon detector. They were originally, the idea for them actually came from studying radiation damage in silicon detectors. And what they found was that when the silicon detectors became radiation damaged really bad, they developed this doped layer, right, around the pixels that started to amplify and give really big pulses, right? But they didn't just break down, they just sort of amplified by a low amount. And they took that and turned that into a feature so that in an LGAD, they have a gain layer, which actually amplifies the signal. Amplifying the signal gives you a very fast pulse. So AC LGADs are a silicon detector that can give you something like 20 picosecond timing resolution. The plan is to build a large area of silicon around in the barrel of the EPIC detector, as well as in the forward region, and use that to provide time of flight. And what you get when you look at time of flight, if you look at the measured beta versus the momentum, you get the separation between the protons, pions, and the kaons, right? Yeah.
No momentum.
But not at high momentum, right? At high momentum, they all start to merge. So what you do is you define, right? Usually what you do is a probability distribution. You look at the performance of the detector and you say, this is the range at which I can identify with a 90% purity or a 95% purity that this is a proton. So when you do particle ID, you're making a statistical statement, right? And you can relax your constraints. You can say, well, I'm okay with 80% purity, or I have to have 99% purity, right? But you can see from the spread on this that you're making a statistical statement, which you can make with very high degree of accuracy at low momentum. But the reason all of these have an upper momentum cutoff is because, again, when they all start moving fast, they're all moving the speed of light. They all look the same. Okay. I wanted to talk a little bit about the data acquisition because I alluded to that in the beginning of the lecture. We can't trigger on the physics processes of interest, in part because many of these physics processes are not triggerable. They're just not separable from normal machine backgrounds, right? So the way to do that is to turn everything on its head and say, fine, rather than trigger, I'll just have the detector send me everything it sees. So each subdetector acts like an autonomous unit that decides when it's hit, it digitizes that hit, timestamps it, and passes it up the data acquisition chain, right? So all of the front end boards on the detector, they're just sending data, right? I don't know, I saw something, here it goes, here's a packet, right? And they're all timestamped so you can put them all back together, right? But that means the data is coming off the detector at something like 100 terabits per second. Right? The data acquisition sees all of this through a set of servers which collect the information and have to somehow reduce this down to a data acquisition rate of about 100 gigabits per second. How do we do that? Well, detectors or in the servers can aggressively zero suppress the data, right? They may look at a hit and go, that's noise, that's garbage, dump it, right? That can get rid of things like detector noise. They can combine the data from the entire detector, which is usually something a trigger can't do. And they can look at the topology of the event and say, oh, that was interesting, we should keep that. But in doing so, they have all of the information of the entire event available to them. And we have new techniques such as AI and machine learning that allow us to identify these events in real time. Right? So within this data acquisition system, we plan to take advantage of heterogeneous computing, which means not just CPUs, GPUs, vector processors, and AI and machine learning in order to be able to reduce the data rate. All right, I'll skip this. And I'll skip this. I talked about detector design and integration. I'm going to take just a couple minutes and talk about some things that I think Todd will talk about, right? Detector backgrounds and radiation, right? So far, all I've talked about was how do I detect the physics I'm interested in, right? But that's not all that happens. Usually what happens is you get splashed with garbage, okay? And you have to be able to survive the garbage, okay? So your detector has to not get radiation damaged, right? And it has to be able to survive everything that's sent by the machine. And the machine doesn't just send you only physics events, right? It's not like if the machine sends you a stream of Pythia events, right? Everything that can happen in the beams does happen, and you're going to see it, okay? So that means not only processes like primary collisions, but synchrotron radiation and beam gas, and we have to design the detector to be able to handle those. Primary collisions are the primary source of ionizing radiation and low energy neutrons. So we look very carefully at the ionizing radiation dose that we achieve. And in fact, you can see that the ionizing radiation dose throughout the detector is actually relatively low. The regions down here can reach maybe 100 kilораds, but even scintillator can handle several hundred kilorad without seeing a degradation. The problem comes when you look at neutrons, right? And this is the neutron flux. And what we do is we convert the neutron flux to the equivalent flux of 1 MeV neutrons. That way I can compare neutron fluxes between different colliders which have different energies. So we convert it to a common basis. Anytime you get up near 10 to the 11th, you're going to radiation damage your silicon photomultipliers. They will begin to draw more current. As they draw more current, they will heat up. As they heat up, their gain will change. They'll be more noisy. They'll fire randomly on nothing, right? And so particularly in this inner region here, we are going to have to worry about the radiation damage that will happen to the silicon photomultipliers in that region. Synchrotron radiation, there are a number of fixes for synchrotron radiation. This is modeled very carefully by the accelerator background group. One of the things that we found we can do is coat the beam pipe in the region of the vertex detector with a 5 micron layer of gold. Synchrotron radiation is very low energy photons. 5 microns of gold almost completely removes most of the hits in the silicon tracker by absorbing those photons. Okay. What synchrotron radiation does do, however, is it has a habit of outgassing the beam pipe for the experiment, right? I won't go into the details on this, but metal tends to adsorb gases, right? Hydrogen, oxygen, carbon dioxide. When the beam pipe is bombarded by radiation, it releases those gases into the vacuum of your machine. Then the beam can actually collide with these background gases. So you have beam gas interactions. In fact, the plan is that you'll actually, not only will you do special things like use special coated pipes and you will bake out the beam pipe with heat, actually the way you get to the best vacuum is actually just burning it off by running machine through it. So this is after 10,000 amp hours. You can see that the pressure in the machine goes down by almost an order of magnitude in the interaction region. These interactions have consequences. The beam gas interaction, so if we just look at one example here, 10 on 100, the EP rate is 184 kilohertz. So at maximum luminosity, we've got 184 kilohertz of the collisions we're interested in. We have 22 kilohertz of hadron beam gas. And you say, well, that's not so bad, right? We have 2,800 kilohertz of electron beam gas, and that is primarily going into our very sensitive electromagnetic calorimeter, right? So we have to be able to handle that, right? And one of the things that EPIC is doing a lot of work right now is studying how to handle that and how that affects our various physics measurements. Okay, I'm over again as usual, so let me just conclude. So I hope I've shown you that modern particle physics detector subsystems are a marvel of advanced science, engineering, and humility, okay? Because you have to accept the things that you just can't get by without and find a way to work around those limitations. There's some beautiful physics in particle detection. I hope I've inspired at least one of you to go into detector physics. There's just some gorgeous physics. Each technology has its own advantages and disadvantages, and there's constant development. The EPIC detector itself is maturing into a detailed technical design, and the key to a successful EIC detector is a combination of technologies that work together to meet the scientific requirements. And the last slide I want to end on is a slide that I actually stole from a talk that Abe gave. But I think it's important to remember that when we talk about technologies and technologies to achieve the science, right, that actually I think a lot of the focus should be on the technologies, because new directions in science, a quote from Freeman Dyson, are launched by new tools much more often than by new concepts. Right? And so the EIC and the detectors at the EIC are those new tools that I think will revolutionize science into the 21st century. Okay, I'm way over, I'm done.
Questions or comments, John?
Yes, John, did the experiments at Hera aid in any way in the design of the?
Oh, yes. Oh, God, yes. So the experiments at Hera, of course, Hera was designed as an EP machine, but there was a lot of things that they didn't know, right? And so the asymmetric nature of the design is much better appreciated. One of the things that Hera didn't have built into it was the ability to use spin. And it later became appreciated how important spin was to be able to unravel things like the structure of the nucleon. So the EIC is, and the detectors are designed from the ground up to make maximal use of spin in making these measurements. The luminosity measurements from Hera, the methods that they use, we are stealing those methods wholesale. They got about a 1.8% precision on luminosity. We want 1% precision on luminosity. When you tell that to the Hera people who did the luminosity measurements, they're like, you guys are crazy. You'll never get there. Right. And it doesn't sound like that big a leap, but it's a hard measurement. So yeah, absolutely. And that's important because Hera was a while ago. Right.
Yes.
And a lot of those physicists have gone on and done other things. And so trying to pull that knowledge back into the community has been really important. Yeah.
Looked like you had a map of the EIC facility earlier showing like the interaction points.
Mhm.
So the EPIC and the potential second new detector, those would be completely new interaction points.
So
Facilities?
there are existing interaction points. So the IP6 interaction point is where the star detector sits right now. And so that would be where EPIC would go. And then IP8, where Phoenix and S-Phoenix sit, would be where the second detector would go, right? Yep.
And is it reusing some of the infrastructure that's already there, or is it kind of just gutting it?
Certainly it's reusing some of the infrastructure to different degrees. Simple things like the building, the crane, the hall, all that kind of stuff can be reused. We'll probably reuse like the cradle and the rails from the star experiment to hold EPIC. In S-Phoenix, they had a complete cryo revamp to handle their superconducting magnet. So certainly some of that money that was invested in infrastructure is going to be reused. And that kind of thing was, part of the argument, right, for building the EIC at Brookhaven, right, was the ability to reuse large portions of the existing facility. That's always a plus and a minus, right? Because you can say, great, I get to reuse this, but I don't get to change it. Right? It is what it is, right? So like if I'm going to take the hole that's already in the ground, I don't get to dig a new hole. Right? So yeah.
I have a question.
Yeah.
So I'm a theorist of my parents. But I was just wondering, looking at detectors overall in the EIC, what's gonna be like, well, if such a thing exists, what's going to be like the big bottleneck there? Anything, or is that just completely depend on interactions?
I can tell you what keeps me up at night.
What's that?
So what keeps me up at night right now is the amount of silicon that we're deploying, right? So right now we're planning to use the ITS-3 sensors. The ITS-3 sensors have just been through one engineering run. They have another engineering run to go through. Nobody knows that there's no guarantee they're going to work, right? And that only gets us the inner layers. We need our own design based off the ITS-3 sensors for the outer layers. So the time to be able to do that is extremely short, right? To stick to schedule. Now, and you look at people usually rate things by the amount of square meters of silicon you're going to deploy, right? And they look at our silicon vertex tracker and they say, it's 10 square meters of silicon. You guys are nuts. Right. And what did we do? We doubled down and we said, yeah, we're going to put another 10 meters squared in our calorimeter. Right. So it's logistics, right? It's very much logistics. You have to look very practically at what can I do in a given period of time. Silicon detectors have a checkered history. They are hard to build and hard to deliver. So that's one of the things that keeps me up at night, right? Yeah.
So if it does fail.
Well, okay. So nothing ever. The thing to remember about a project like this is it's very rare that something just fails, right? That you come in, one morning and you get an email saying everything burned down, start over, right? That usually doesn't happen. So what it then becomes is, so for example, to go forward to CD2, we will have to have a fallback option, right? There are a number of possible fallback options, right? We may not, for example, we may have to back away and not use silicon detectors. That will have a physics impact, right? Whenever you have to do something like that, it almost necessarily implies an upgrade, right? So anytime you have to descope, you have to back away from your technical goals for realistic reasons, then it implies that at some point in the future, when that problem is solved, you're going to want to buy it back, right? So that's the right way to look at it, right? If you have to back off on any of your technical requirements because they're just not ready, Usually what happens is a group of physicists will immediately bud off and start writing the proposal for the upgrade. Right?
Yes, and you mentioned for the silicon detector readout that it will integrate over 200 bunch crossings, and you'll use some other detectors to distinguish between these. And I was wondering to what uncertainty this leads and how you will determine the uncertainty. So I'm a theorist.
Yeah, right. A question on uncertainty coming from a theorist. You're exactly right. So one of the things that we're studying right now is how much do we need in terms of pattern recognition capability to be able to limit that ambiguity, right? At some level, bad things will happen. At some level, you'll get a random hit that will overlap and you'll pick up a fake track, or you will lose a good track because of an inefficiency in one of these outer detectors. And so what we're trying to do right now is decide at what level we can quantify that and what level we're willing to live with. That's hard because now it's not just simulating a Pythia event, but we have to take a Pythia event. We have to mix that event with all the synchrotron radiation that happens, right? So now it's not just an event, it's an event at a given luminosity. And then we have to mix in the beam gas that would happen. And we can't, for most of the physics results for the proposal, we did what's called truth tracking, right? Which is we look at the hits and say, they belong to that track, we fit it, go, there's the momentum resolution. You don't get to do that for real, right? You have to actually find the tracks. And you have to find them in this mess. And answering that question has to fold in your ability to find them. And so we're having to now actually write all of the software and do all of the studies as realistically as possible. And there's a lot of ambiguities, right? Is our model of the synchrotron radiation right? Yeah, right? So we try to be conservative, right? We try to take the worst limits that we reasonably find. So I don't know the answer to that yet. The answer is going to be, we're going to try to limit it to a level that it doesn't interfere with the physics, and we can still afford it. Yeah.
Regarding the hoped for second detector, would that be something similar to the EPIC design, or would it be something maybe like a built around a time projection chamber or something like that?
I doubt it'll be built around a TPC simply because a TPC integrates over even longer time than a silicon detector. The SFenix TPC has like a 16 microsecond integration time, right? There are ways to live with that, but that's just my opinion.
Okay.
But let me just comment on the second detector. I should probably have Alexei stop the recording.
Appropriate points in the lecture.
So one of the things about the EIC, so there's some things you have to realize about the EIC. One is the EIC includes the ability to collide at two interaction regions, but only the money for one interaction region, right? So you have to buy all the magnets and the crab cavities and everything to get collisions at a second crossing. That's about $180 million. Okay. So before I can start talking about a second detector, I need $100 million, right? Now, what do I need for a second detector? Maybe another 300 million. Right. So I'm not saying this to be negative. I'm saying to say that there's a threshold, right? Would you build another copy of EPIC to do exactly the same thing? Absolutely not, right? It just doesn't make sense. It's a waste of resources. So a second detector is going to have to bring something to the table, which is fundamentally new and interesting. It should have overlap with the EPIC detector, but it should also be able to do something new. And one of the things that the second interaction region has is a larger angular crossing, 35 milliradians. And that allows you to go to, it allows you to go to smaller values of T. T is the momentum transfer that proton, let's say from a DVCS gets. You can go to smaller measurements of the kick because you can measure down, right, to closer angles with respect to the beam. Is that enough? I don't know. Right? There are people who are working to see whether or not that's enough. It may take some fundamentally new ideas. One of the other aspects of the second detector and the EIC is that the luminosity is shared between the two beam interaction regions, right? That's not true at RIC, first order, right? If SFenix runs or STAR runs, they both get the same luminosity, right? Based off of the optics at their IR. At the EIC, the only way you can make that work and have the beams maintain high luminosity and not blow up the bunches, and Todd will probably talk about that, is to have alternating bunches collide at each IR. So now the bar is higher. Because remember, luminosity is running time is money. So you have to have something that says, not only is it justified to build this, when there are so many other priorities in nuclear physics, but I'm perfectly justified in stealing half the luminosity from the first detector because the science is so compelling. And I'm not, to anybody listening to the recording, I'm not saying this to dump on the second detector, right? I think we all realize that there's an enormous amount of advantage to having physicists look at the same thing in different ways, because that's how we catch mistakes. It's how we catch errors in logic. But there is a hurdle here, a very real hurdle. And I'm actually really looking forward to seeing what the people working on the second detector will come up with. They have advantages. They have 5 more years of R&D to work with, right? They may be able to deploy technologies that for us right now are just, can't do it. It's not ready. So I think it's something exciting to think about. And again, it's exciting to think about because of the constraints, right? Because it's complicated and difficult. Does that help?
Yes.
Okay.
Thank you.
Good.